nanohub.org.
Online simulation, and more for nanotechnology.
Welcome everyone. Welcome to our latest NanoHub tutorial. My name is Arun Mannodi Kanakituri. I'm an assistant professor in materials engineering at Purdue. And it is my pleasure to invite for today's workshop tutorial Dr. Chen from University of California, San Diego, UCSD. He is an assistant project scientist there in Professor Xiuping Ong's group at UCSD. Dr. Chen received his PhD in 2016 in mechanical engineering from the Hong Kong University of Science and Technology. He joined Professor Xiuping Ong's group as a postdoc at UCSD, and now he's an assistant project scientist. His work focuses on computational material science, materials machine learning, and materials-related software package developments. His expertise includes machine learning force field developments and the construction of quantitative structure property relationships using deep learning methods, especially graph networks. So today, Chen is going to talk about constructing quantitative structure property relationships via material graph networks. And if you need any info on, instructions on creating your NanoHub account and slides for that, Jared has posted that in the chat in case you need that. So with that, Chen, please go ahead.
Yeah. Thanks for the introduction. Good afternoon, everyone. And for those who are the same as me on the West Coast, good morning. So today I will introduce to you our recent research on materials graph networks, and also to perform a tutorial on how to use the package that we developed for constructing graph networks to predict materials properties. And to begin with, constructing the structure property relationship has always been the central goal in material science. About 100 years ago, Paul Dirac has famously said that the underlying physics law necessary for the mathematical theory of a large part of physics, the whole chemistry, are thus completely known with the discovery of quantum mechanics. However, he also noted that the difficulty is that the exact application of these laws leads to the equations are much too complicated to be solvable. And unfortunately, this is even true after about 100 years. And nowadays, even with the approximation using the density functional theory, the ab initio calculations are still too slow to run on a large scale. For example, when we evaluate the thermodynamic stability of a new material, those calculations can take us about hours on a supercomputer. And for more advanced properties, like the dynamic stability using the phonon calculations, those can take probably days. And also, what we usually do in our lab is to calculate the diffusivity of a material. And for those calculations, we typically need to calculate a variety of temperatures. And those can easily take weeks on a supercomputer. So fortunately, with the recent development of data science and machine learning, we are shifting our research from computational-driven science to data-enabled science. In material science, this is shown by the paradigm as I show on the right. Well, existing computations and experiments have already produced a substantial amount of data. And with those data, we can construct surrogate models using data science or machine learning. And next time when we have a new structure or new molecule structure, we can use our surrogate machine learning models to predict the properties directly within sub-second speed on our laptop instead of going to the supercomputer. So the machine learning is the study of computer algorithms that improve automatically through experience. Here, the experience is just the materials data that we already have at hand. And the eventual goal would be using machine learning with the materials data to construct such a model that can replace or accelerate the experiments or ab initio calculations. The machine learning, some people who are not familiar with machine learning may be scared by this word, and they may think machine learning is something that only exists in computer science. In reality, as a material scientist, we can just treat machine learning as a glorified code fitting and pattern recognition. Essentially, we're trying to model this behavior that map the input to the output, right? So here the input is usually our structure of material or the molecule structure, and the output would be the property that we're interested in. For example, the formation energy, the band gap, etc. And nowadays, machine learning has been used in many different fields and has revolutionized the way that we interact with the outside world. For example, now we can, on Netflix, the algorithm will automatically recommend the different episodes to us. And also we are seeing the self-driving cars and those fancy models that can beat the best human performance on the game of Go. In material science, there are generally two directions of how we do the materials machine learning. The first direction is to construct so-called compositional models. So in those models, instead of describing the materials as a complex object, here we are only using the compositional level information. For example, given a structure, we just take the formula and then we calculate the aggregated statistics on the properties of elements. For example, for the iron oxides, ammonia oxides, we just take the average atomic mass for this formula, or we can also take the average column and the periodic table for the elements in the composition. So surprisingly, such models have shown very good performance when they predict some basic properties. But one of the issues is that the composition models cannot distinguish the polymers. For example, given a graphite and a diamond, we know that both of them have the same carbon composition, but in reality, their properties are vastly different. And one is a very soft material, and the other is a super hard with a wide band gap. And here, if we just use the compositional models, for sure we cannot really predict the distinct properties for graphite and diamond. And the other line of thought is to use the so-called structural models. So for those of you who have attended the talk from last week from Yunxin in our group, he introduced the machine learning interatomic potentials. So in such kind of structural models, one just calculate the fingerprints that describe the local environment of an atom and eventually to describe the overall structure. And then using those fingerprints, we combine them with machine learning models. In such way, we will be able to construct a very accurate model to describe the potential energy surface. And unfortunately, as you may also notice in the last talk, such applications is usually limited to a small number of elements. So you have to train one model at a time for individual chemical space. For example, you have one model for molybdenum and one model for nickel moly system and one model for lithium nitride system. So those are like case by case. And there is no such thing called a universal machine learning model that you can use to predict all of this, all the elements and all the crystal structures in the SSD or known material space. Today, what we are going to talk about is the so-called graph networks. It's a structure-based machine learning algorithm. So the core idea is given a structure, we try to represent such a structure using our graph, where in this case, the atoms will be the nodes of the graph and the bounds will be the edges of the graph. So during the computation in the graph networks, we will propagate information from the nodes or the atom to the neighboring bounds and also eventually to the neighboring atoms. So such operation is performed locally, and that's why sometimes people call this as a graph convolutional neural network. So it's basically convolution operation that is applied to the local structure of the graph. And after a few iterations of convolution, will eventually arrive at the output graph. So this output graph is more encode more abstract information of the input structure. And afterwards, we compress the output graph to a feature vector that represent the structure, that represent a structure or molecule. And once we have the feature vector of the structure, it's very easy to map this vector into the target variables using feed-forward neural networks or any other means. And as you can see, that all this description is relatively general, and I do not specify whether this apply only to the structure or a molecule, or I also did not specify that this only apply to a certain elements. So the reason is that such approach and such a representation can be relatively can be actually very transferable in the sense that I can apply this to all the structure and all the molecules. And as I will show later, that such approach is also very accurate and can be applied to all sorts of data sets. So the graph is at the core of this approach. So here in our approach, we have a slightly different definition of the graph. In addition to the nodes and the edges represented using the atoms and the bonds, we also included something called the global state. So the global state is, in the global state, we put the information that is independent of structure. That can be external conditions, for example, the temperature, the pressure, etc. And for description, we use Gaussian expanded distance. And for the atom, we just use the atomic number as the atom representation. So during the graph convolution, we first update the bound information by including the neighboring atoms as well as the global state and the previous bound state. And then we update the atom state and eventually the global state update. And here the phi's are approximated using the artificial neural networks because those functions are universal approximators we can use to approximate almost any continuous functions. So that explains one of the graph operation, and in reality, we have to stack many layers of this graph convolution together. And so here are the building blocks of the materials graph networks, or magnet for short. And as the implementation has already been open source on our group GitHub webpage. Okay, once we have the model, the first data set that we use is the so-called QM9 molecule data sets. So such a data set contains more than 130,000 molecules and more than 13 different properties calculated on each of the molecule. And we perform a training validation and test split using the 80%, 10%, and 10% split. And so I want to emphasize several metrics here is the internal energy, the free energy, as well as the HOMO and the LUMO values, and the thermal capacity. So here, the magnet model that we construct in this work has achieved a relatively high accuracy compared to the previous works. And for those properties, it even exceeds the chemical accuracy. The chemical accuracy are the error between the calculation and the experimental values. So those are the best value that you can achieve using any kind of initial calculations. And overall, for the 13 properties, we have achieved the state-of-the-art performance on 11 of them. And maybe this value have changed during the past years. And since those are already the metrics that are from 2 years ago. And if we just, as mentioned earlier, if I just use the Z, the atomic number as an atomic feature, still the magnet model are actually quite accurate. And then in addition to the molecule data sets, we also move on to the materials project crystal database. So for that database, it contains almost all the crystal structures that we know, and also with the density functional theory calculated properties. So we apply our magnet model to the formation energy, band gap, elasticity, as well as some classification tasks. And we find that the magnet model can achieve consistently high accuracy in all those properties. And then afterwards, since we have the infrastructure, we are trying to use the infrastructure to solve a more challenging problem in material science. And one of the problems is that in material science, we usually encounter the situation where the very high accurate data set is usually very small, while the very inaccurate data are actually pretty large. So this is best explained in this case for the band gap, where we can see that the very cheap and the large data sets is the PBE from the PBE functional calculations, and this data set is huge. However, for more accurate functionals, for example, the HSE, the GLLBSC, the scan, and especially the experiments, the data set is considerably smaller. And very naturally, it brings us to think, can we use the large but less accurate data to improve the model prediction on the small but accurate data, or the high fidelity data? So if you remember previously in the graph networks, we have encoded the structure independent information to the global state. And here the fidelity information itself is not really relevant to the structure. And hence we can encode the fidelity information as a categorical variable into the global state of the graph networks. By using such a simple approach, we are able to incorporate the properties calculated from different sources or even from experimental measurement into one single model that we can predict the very accurate property of the material. So here I'm showing you the model performance on including different number of data fidelity into the one single model. For the one fidelity model, which means we train one model individually for each of the fidelity. So here, those are the errors. If we incorporate like a low fidelity data into the model, so here the low fidelity is the PBE fidelity. We can see the model errors on the high fidelity task. For example, the GLBSC, the HSC, and the experiments are reduced substantially. And we also, going forward, we also include the full fidelity into the same single model. We see that the model error on the high fidelity task also further decreases. So that's all for the model metrics. So next, I'm gonna lead you to the NanoHub resource. So if you can open the NanoHub with me. Oh, so before I go to the tutorial session, any questions from the audience? No? No questions? Okay, so let's go to the tutorial session. So if you open the magnet tools, this is where you'll be looking at. Here I'm going to show, first I will still do some introduction of the mechanism of how do we construct the graph networks. Then I will go to introduce to you how can we use the pre-trained models that we can directly use out of the box to predict the properties that we are interested in. And then I will go to show some examples of how do we train a molecule model, and also our crystal formation energy model using crystal datasets. And lastly, I will give a tutorial how do we train a multi-fidelity.
Sorry to interrupt. Hi, sorry to interrupt. I don't know if it was just me or everybody else made the problem. I didn't see any content on the screen.
I was just going to say, are you showing something, Chen? Because the screen is empty for us.
Oh, okay. Let me.
Maybe yeah.
I will end the slideshow and then switch to the.
And for the attendees, if you have questions, you can put them in the chat.
Yeah.
Or if we take a break during the tutorial, we can answer you can ask them at that time too. But please put the questions on the chat.
It may be better actually to put them in the Q&A. Because
in the Q&A,
then the panelists can see them.
That's right. That's right. Yeah. Thank you. Yeah. Thank you, Jared. Yeah. Put questions in the Q&A. Yeah.
Can you see the screen now? I suppose so, right? The Google Chrome.
Yes, that's better.
Okay. Sorry about that. My first time using this function in this software. So this will be our tutorial session. Well, I will first give a short introduction of the mechanisms of constructing graph networks, and then I will go to the using the pre-trained graph models. We actually shared all the trained models, as you said earlier, on the matrix side, and those models can be used out of box to do a new prediction of new molecule or new crystal structure that you have. And then I will show you how do we train a new molecule and our new crystal models from our materials data sets. And lastly, I will do some tutorial on how do we train a multifidelity crystal bandgap model, as I showed earlier. So the materials graph networks is actually an implementation of a graph networks that is recently summarized by the people from DeepMind. So they have a very nice overview of summarization of a summary of all the different graph approach, and then put them under one umbrella of graph networks. So the graph networks, the motivation of that work is that so for all the artificial intelligence, the combinatorial generalization is the top priority. So that essentially says, how do we use a limited number of examples to learn from them, to learn the relation between them, and then apply the learned rules to unlimited number of instances or observations. And in the work, they argue that the structure, the representation, and computation are key to realizing these objectives. To understand the rational reasoning behind this, they defined a few quantities. One is called the entity. Entities are elements or objects with attributes. So in our case, it's just the atoms, right? The atoms are the entities. And the relation is the property between the entities. So in our case, the relation is just how do we form the bonds between the atoms. And eventually the rule is the function that maps the entity and relation to other entity and relations. So in our case, it's just the graph convolution. And there's a core concept called the inductive bias. So the inductive bias is the set of assumptions that the learner use to predict the outcome of a given input that has not encountered. So you may not have noticed, but every time we train a new model, we actually have having inductive bias. For example, when you train a linear model on the data sets, how do you know that the data sets follow a linear relation? So those are the inductive bias that we pose on the data sets. Various deep learning models have their own characteristics and their own inductive bias. So for the fully connected neural networks or just the artificial neural networks, the inductive bias is relatively weak. So we are saying that all the input neurons can be linked to the output neurons. So there is really no strong inductive bias here. For the convolutional neural networks, we are saying that the relationship is relatively local. We are applying a convolution operation to a small local sample of pixels, right? So the inductive bias is that the relationship is relatively local. And for the recurrent neural networks, we are saying that the input follows a sequence. So there's a sequentiality in the inductive bias. And for the graph networks, we are essentially saying that all the nodes and are connected. The nodes are connected using from the edges, and the inductive bias is relatively arbitrary. And it may be surprising, but the graph networks is you can actually project many relationship onto the graph networks. In our case, we are saying that a molecule structure or a crystal structure can be projected to a graph network. And in general physics, a mass spring system can also be a graph networks. Even the n-body system, we are saying that the interaction between the different bodies, they are, you can think of them as connected by some edges, and then they can form a graph, and then so on and so forth. And in there, we also follow the original graph definition by including the global states in the graph representation. And the updated steps are actually the same as what they proposed in the original work. So that's how we had the idea of materials graph networks. Is essentially our implementation of the graph networks from the DeepMind. And that's for the intro. And let's go to the pre-trained model. Can you see this? Yeah, actually, this morning I noticed that maybe many people are using the tools at the same time, and we had some issues with the running TensorFlow. So maybe you can download all the repo and then run this locally on your own computer, and those will give you the same results. So here, the magnet is the tool that we use. It's called the materials graph networks, and then you can import the model itself. It's called the magnet model, and loading a pre-trained model can be as simple as calling just one line of code. It's just a from file, and we have shared all the pre-trained models in our GitHub repository. If you have time, you can go there and then download all these models to play with them. And once we have the model, we still need a structure, right? So here to load the structure, we use the Python material genomics or the PyMagine package for load the zip files from local disk. Now here I'm showing you a simple example of sodium chloride, and here we loading the structure from a local zip file can be also as simple as just one line of code. And afterwards, we use the model to predict the structure. And from that prediction, we can get the formation energy per atom. And in this case, the formation energy per atom for the sodium chloride is negative 2.09 eV per atom. And if we go to the materials project website and we check the formation energy per atom calculated using DFT, those values actually match pretty well with the magnet predicted values. So it's not surprising because the model was previously trained on the materials project data. And similarly, we can use the bandgap model. And first we load the model, the bandgap regression model, and then we predict the bandgap of this crystal structure that we just loaded. And here the bandgap value for sodium chloride is predicted to be 4.886 eV, and it's also quite close to the value that we have on the materials project database. So we also include the elasticity model. Again, this value, the prediction process is the same as previous one. And one small subtlety is that here, instead of feeding the bulk or shear modulus directly, we have chosen to fit the log 10 of those values. And eventually, if you want to predict the elasticity property of the structure, you have to convert the quantity back to the bulk modulus and shear modulus by taking the 10 power of them. Again, this value, the elasticity values actually match pretty well with the reality. So, and we also, this should be 4, and we also have a internal energy model for the molecules. For the molecules, the APIs or the application programmable interface is the same as the crystals. So essentially, we just construct a molecule, and then we load the model from the pre-trained repository, and then we predict the property of this new molecule. So that's pretty much for how do we use the pre-trained model. It should be relatively simple to catch, right? Are there any questions on this side? No? No questions on this?
Chen, if you're answering questions, you can take a look at some of them in the Q&A.
Okay. Let me see if I can find them.
If you click on the three dots, more options, Q&A.
Actually,
yeah, I got a question from the Q&A. It's well known that the accuracy of the band gap with DFT is very poor. What level of accuracy for the band gap did you get with the graph neural network, for example, for silicon?
Yes, at the graph networks, it cannot really exceed the density function theory in terms of accuracy, because the graph networks here we are training the model on the DFT data, right? It has to be worse than the DFT. For the silicon, I remember that we get a 0.7 or something EV from the graph networks, and also that value is of course is smaller than the true value of 1.4 EV, about 1.4 EV, if I remember correctly. Yeah.
Yeah. Thank you. I remember that the overall accuracy for the band gap is 0.3
EV.
Yeah.
Yes, correct. So that error is with respect to the DFT value, and the DFT value, in this case, the PBE functional has an error about 1 EV with respect to the experimental results. So there's two different types of error source in the overall prediction. If you're comparing the prediction value to the experimental value, that's why we have this multi-fidelity graph networks, where we also include some of the experimental value. We're trying to use the low fidelity PBE data to improve the model performance on the high fidelity task.
Yeah, thank you.
So let's go to the training on molecular internal energy model. Well, here first we need to load the data. Here the data has already been saved on in the repo. Basically, it's just the key value pairs or the dictionary. The key is the QM9 ID for the molecule, and for each of the QM9 ID, we have the molecule object dictionary, and we also have the properties and also the SMILES representation. It's actually a string value for representing the molecule. But we don't really need those for now in this model. And basically the way that we construct a graph network model is first we read the data. The data consists of structural objects and as well as the target properties. And as you can see, the molecules are read using just a simple line of code, which we loop through all the QM9 IDs, and we get the molecule objects. It's a list of molecule objects. And then we also have a list of target properties. In this case, we just take the U0 value out of the property list. And the overall number of molecules here is 100. So I deliberately choose a small number so that you can run on the notebook, but unfortunately it cannot run today. Maybe you just download them and run it on a local computer. And then normally we would split the data into train and test using some kind of random split or some other method that you prefer. And here I'm splitting the train and test using 80% and 20% ratio. And the way that we construct the magnet model is by a few steps. So first, you probably remember that in the representation, we are trying to compress the structure into a vector. And in that case, In that case, if we double the size of the structure, then we have to make sure that the structure vector does not change, which means we are essentially predicting an intensive property. For the extensive property, we have to multiply the output by the number of atoms. So that's the major difference between this model and other models. And we have to tell the model that, okay, the U0 is an extensive quantity, which means we have to multiply the output by the number of atoms eventually. And then we have the scalar for the targets, and we construct a graph converter. The graph converter is how do we calculate a graph from the molecule or the crystal structure. And I know here I use the Crosscrystal graph. It's only because as I mentioned earlier, this model is quite transferable, and the Crosscrystal graph here means that I can just take the atomic number from the atom or the elements as the inputs. So such approach can be applied to molecule as well. That's why here I'm just using the crystal graph. And the last step is how do we construct a model? It's actually one simple line of code. We specify the graph converter, and we also specify the centers for the Gaussian basis for the expansion of the distance, and we also specify the Gaussian basis weight, and we tell it the target scalar. So that's how we construct a simple magnet model. And surprisingly, even with the simple construction, we can train the model relatively effectively. So it's we can just call the model.train and the train molecule and the train targets, and we specify the number of epochs, and the verbose controls how much information that we want to output when we train the model on the fly. And once we have trained the model, we just predict the molecule property from the test data sets, and we plot the predicted value for the test data set and also the true test targets. And as you can see, that using such a very simple construction, this molecule model can capture the trend relatively well. So that's all for the molecule model construction. Any questions? No? So
yeah, I got a question from the Q&A. What do you think is the reason that the classifiers are doing worse than those in CGCNN?
Yeah, that's a very good question. In fact, if you read the CGCNN paper, you will notice that they have an extra data filtering step. So the data filtering step, they eliminated all the crystal structures that do not have the band structure calculated. But in the magnet model, I actually did not apply those filters. I just use all the data that we have, and presumably those without the band structure calculation will give you a slightly different results. Yeah, because sorry, I have to mention that there are two ways to calculate the band gap. One is from the band structure calculation. The other is from the density of state calculation. And for the CGCNN, they use the data exclusively on the band structure calculation. But in our case, we did not perform that filtering. We just use all the data. So there is, I think the data quality is sort of lower than what the CGCNN have. Yeah.
Okay, thank you.
Okay, let's go to the crystal formation energy model. In this case, I prepared a more realistic data sets. Here, I queried all the ABO3 materials from the materials project. So we know that the famous perovskite material have this kind of formula, right? And so the total number of data points is about 2,400. And again, we first construct the structure object list and also the property list from this data set. As you can see, I also show the distribution of the data, and it has a relatively nice Gaussian-like distribution in this case. And again, we split the data into train and test by 80% to 20% split, and using the same model construction process, we are able to construct a magnet model. you may notice that this process is almost identical to the molecule. That's why, again, I have to emphasize the transferability of the magnet model. So you can essentially construct the exact same type of model for both molecule and the crystals. And since the formation energy per atom itself is an intensive quantity, so we don't have to convert it by any means. And I also have an additional input parameter. It's called the number of blocks, because this data set is relatively large, and I have to reduce the number of convolution blocks to make it accessible on my laptop. And so the training of the model is still the same, and I trained the data for 5 epochs. And lastly, we've just predict the test structures. Again, as you can see that by training such model by only 5 epochs, we are able to predict a quite nice trend. Although the energy range is vastly different, that's probably because for one, I only trained 5 steps, and for the for 2, this data set is still relatively small. And as you can see that I did not constrain any elements. It's different from the molecule data sets, because the molecule data sets, we only have the carbon, hydrogen, nitrogen, oxygen. And here, the ABO3 data sets, we can potentially have all the metal elements in here. So it's a much larger chemical space to work with. And that's why our model performance is actually relatively weak in this case. But still, we are able to capture this trend in the data relatively well. So any questions on the crystal models?
I have a question from the Q&A. How do you think graph network can be applied to crystalline materials? That is where the features are size, orientation, and shape of each grain.
Could you please repeat that again? The crystal material with different size. You mean a pretty large
where the features are for example, the size of the grain, the orientation of the grain, or shape of the grain.
Oh, okay. So that belongs to a different regime. Basically, here we are dealing with we are just using the atom as nodes and the bound as edges. Maybe in that case, you may need a different definition of your graph, right? In that case, you will have a relatively large system. It's not just like hundreds of atoms. Probably you have thousands or tens of thousands. And theoretically, you still can use the magnet, but then you have to have the sufficient data to work with. And in that case, I would say it probably is not an ideal scenario for application of the magnet that we show here, that you can develop your own way of encoding the materials using a much simpler approach.
Thank you.
Okay, so let's go to the multifidelity networks. So here, the multifidelity cross-crystal networks is the one that we showed earlier in the slides. And then we first load the data, and then we here we have to specify the two different targets. One is the PBE bandgap, and the other is the GRBSC bandgap. So those are like two different. You can treat them as two different data sets. And we can see that the PBE data set is slightly smaller than the GRBSC. And the key point here is that when we are doing the structure graph calculation, we have to tell the model that one type of data has a different state, right? As I mentioned earlier, here I'm encoding the PBE to a state of 0 and the GRBSC to a state of 1. And in the same time, we have to copy the structure twice if we have a different targets. And then we split the data again, the same as before. And here the construction of magnet model is slightly different. We have to tell the model that there are two fidelity of data, and we want to embed the fidelity into a 16-bit vector. All the rest are almost the same. All the rest are the same. Yeah, that's the only difference here. There are difference in the data construction and also the slight difference in the model construction. Then we can train the model the same way as before. See that loss actually reduce over time. And we predict the model and predicted the data on the test data sets. And here again, those are the test parity plot. And again, I would like to also show that for the same structure, you can actually predict two different properties depending on the state of the structure. So for example, I load this structure, and if I set the state equal to 0, which means I'm trying to predict the PBE bandgap, then I get this value. And then I can also set the state to 1, which means I want to predict the GLB-SC bandgap, and the model will give a different results. And that's how we work with the multifidelity models. And all those packages has been open source on this GitHub repo, and you may want to check it out if you're interested. So any questions on this side?
Yes, I have got a question from Q&A. When doing the machine learning calculation, can you help the DFT poorly calculated bandgap with some experimental references? Let's say using other materials for which the bandgap is well known and very accurate.
Yes, that's definitely the case. That's definitely one of the things that we try to solve using the multifidelity. Essentially, we try to combine different sources of the data, but they are the same type of properties. Then we try to combine them to improve either the calculation or the experimental predictions. But for improving, in your case, you have the calculations and the experiments, and theoretically we can include both together if we have a large enough data, and then next time we have a calculation that we want to perform, we can just use the model to predict the experimental bandgap of this material. Yeah.
Okay, thank you.
Any other questions?
I have got another question from the Q&A. On your presentation slide 16, you mixed the different methods. Each method predicts property with different results. How did you deal with these differences? For example, your graph model and expected prediction.
Well, actually, you can see it as the model itself can predict all the different levels of fidelity information, right? And then we just compare the same type of functional to the same type of prediction. For example, we compare the PBE bandgap, the calculated PBE bandgap, to the predicted PBE bandgap. It's like for one single model, we can choose to predict a different functional output. So there is no comparison between, for example, the PBE and our experiment. So those comparisons are meaningless in this current setting, right? We compare the PBE to the PBE prediction. We compare the experiment to the experiment prediction, and that's it.
All right, thank you. And another question, is there a reason for the current sequence of updating the features from the item type to bounding information? What impact does the sequence make?
Yeah, that's actually a very good question. I thought about this. If for example, if we you can swap the sequence, and that shouldn't be a big deal. And I personally haven't tested it yet because there is a very nice sort of a linear workflow if we go from age to nodes and to the global state. And theoretically, you can do it in other sequence, and it shouldn't really matter much.
Okay, thank you.
Mm-hmm. Any more questions?
So Chen, is that the, are you at the end or is there more?
Oh, actually, this is the end. Yeah.
Okay, so we are at the end.
Yeah.
Okay, thank you very much then thank you very much, Chen, for the wonderful presentation. I hope people were able to follow along, and in the Q&A we got a lot of questions, so thank you very much to Yuxing for saying out loud all the questions. So I think you were able to answer most of them. If you want to take a look at the Q&A, you can click on the more options and take a look at the Q&A. If there is something else remaining there that you would like to answer, there are a number of questions there, although I believe you have answered most of them now. So there is a question that says, can I follow up about using known physics on the graph?
What kind of physics is that?
Yeah, if I think Juan Nino, who asked the question, I believe you can also unmute yourself and ask a question out loud. Oh, do we need to unmute you?
I think the host will have to do it. Ollie's got the host role right now.
Okay, yeah. Ale, can you unmute Juan Nino?
I'm on it. Give me a second.
Okay, thanks.
Jared, this is your fault for giving me control.
Sorry about that.
I'm getting there. Sorry. I got you. Unmute.
Hey,
There you go.
there you go. Good. So you can hear me. Good. So what I was mentioning is early on, and I'm not too familiar with how you convert the structure to the vector for the graph. But the question that I had is whether you use any known physics. So, for example, using symmetry and use, for example, an asymmetric unit cell, or using a Wigner-Seitz cell, which would make your vector probably simpler and therefore simplify your calculations. If you're taking your structure, for example, rock salt, how many atoms do you actually use to describe the rock salt, the sodium chloride that you presented, right? Is it 13 atoms? Is it just 2 with their typical bond, and then you extend, in all 3 directions? Could you explain on that?
Yeah, actually, in reality, that actually doesn't really matter much. Both of them will give us the same output vector because the magnet construction as of now predict intensive property. So no matter how you multiply your cell, eventually you get the same structure vector. Although I agree with you that the computational complexity for a larger cell may be more maybe higher, but that was not our concern at the moment. Yeah. There's only a slightly increase in the computation of graphs, so that's not the key issue here.
Okay, thank you.
Are there any more questions? We can unmute others if necessary. I think there were some questions about, the band gaps and, the difference between the experimental and, different levels of computations. Is there any multifidelity done on training the difference between experiments and computed?
Here, actually, in the backend model we showed earlier, we have the experimental and the computation in the same data set. Yes, that's a viable approach to improve the model performance.
Okay, okay. So that is done. Yeah.
Mhm.
I believe the other questions in the Q&A have been answered. Are there any more questions from the general audience? If not, I think we can wrap it up then. All right. Yeah. Oh, okay. This is a question actually. Give more weight to known accurate experimental data.
Yes, yes. That's of course, yeah, we have the capability to specify the weight for each of the data points.
Okay, yeah. Yeah.
Yeah.
Okay, so let's thank Dr. Chen again for the great talk and the great tutorial, and people can follow the notebook and play around with different things afterwards. And thank you very much also to you, Xing Zhuo, for answering a lot of these questions and for reading them out aloud. So thank you very much, and see everyone at the next workshop. And thank you to Professor Straka, and thank you to Jared as well. Yeah.
Thanks, everyone. Thanks, Xi. Very nice.
Thank you.
Thank you.